Okay.
Yep, thank you.
Okay. So that's how much time I have? Like 15 minutes. Okay. Okay. So hi, thank you very much, organizers, for inviting me. Give me pleasure to give. Yeah. Anyhow, I'm grateful for allowing me to give a talk in this conference. So that, as you see on title, it's the talk is going to be about the geometry of simply connected wandering domains. You've heard a lot about wandering domains already in the morning session with 3 talks. So I will sort of just briefly skip or say a few words about what is known, but I mean, most of it you have already heard. Then we'll get to the main theorem and the sort of the sketch of the proof. Let me see if I know how to go. Yes. Okay. So we consider the dynamical systems given with by the iterates of entire function. So a function from C to C. And just recall basic definitions, as you all probably know. So the Fatou set is a set of all points that have a neighborhood on which the family of iterates is a normal family. And the Fatou component is a connected component of this set. So a Fatou component is called pre-periodic if sort of the forward orbit does not self-intersect, actually. And the other orbits that are not pre-periodic are called wandering domains or wandering components. And the classical goal, or one of the main goals in complex dynamics, is to obtain the complete classification of all possible Fatou components in terms of their dynamical behavior, or I don't know, their geometry and so on. And okay, so you don't see the title above. So in terms of their dynamical behavior, we have good or almost a complete classification of in many cases of Fatou components. For example, we know we have complete classification of pre-periodic Fatou components. Now this is due to Fatou and examples of Siegel and Baker and so on. So you can have attracting domains, you have parabolic domains, rotational domains, and so on, or things that go escaping domains. A lot was said today about the multiply connected domains as well. So it was talked by Bergweiler, and I think Thaler also said something about it. So the dynamics in those domains is well classified, and you've also heard in previous talks the classification or the possible dynamics inside the simply connected wandering domains, right? So, and the dynamics was classified in terms of hyperbolic metric or the distance of the orbit. I mean, if you compare the distance of the orbit towards the boundary. Okay, so I'll try to skip that because this was sort of everything was already set in the morning, so we'll try to not double. Just a few more definitions just to recall. So escaping wandering domain is a domain where if you take an orbit and any point of its domain, the forward orbit leaves every compact set. So the oscillating one is one that you can have orbits converging. So subsequence of the orbit that converges to infinity, and there's another subsequence which converges to a finite point. And dynamically bounded ones that sort of every forward orbit is bounded. And many of you know that there is a major problem or open question: does there exist an entire function with dynamically bounded wandering domain? Okay. So this is more or less about the dynamics and the behavior of wandering domains. But this is not the main focus of today's talk. So in my research, I tried to focus on the geometry of wandering domains. And I got to the following the following result, and I'll try to explain how I got it and what's the idea behind the proof. So the theorem says that let omega be open, so bounded, connected, regular open set whose closure has a connected complement. Then there exists an entire function f for which omega is an escaping, or you can also make it oscillating, wandering domain, and the iterates on omega are univalent. Okay, so let me just go through the conditions on the set. What does it mean to be regular? So set is called regular if and only if U coincides with the interior of its closure. So for example, look at this domain here. This is like a unit disk, and you remove just one hair or like a line. So this set is not regular, because if you take a closure, this thing is vanishing. You take interior, you end up with a full disk. Okay, so this thing is not regular. And the other one, the other condition is that the closure has a connected complement. For example, this guy here, this set does not satisfy this condition. If you take a closure, you have this earring, and the complement has so the outer part and the inner part. So this is also bad. Okay. So yeah, but I mean there are a lot of sets that there are a lot of sets that satisfy these conditions. In particular, every Jordan domain, any boundedly connected Jordan domain satisfies these conditions. For example, you can have a wandering Poland if you want, right? So this is the outer shape of the Poland. I googled it, so I hope I found the correct one. And this precisely can be a wandering domain. So that's what I'm trying to say. So it's a natural question whether or not these conditions are not only sufficient, but as well necessary conditions, or am I just sort of making conditions up and so on. So the condition omega on omega, that omega is regular set is not only sufficient, but also a necessary condition. And this can easily be verified. Just quick sketch. So suppose you have a wandering domain, omega, which implies that if there's a wandering domain, then your for two set is going to be disconnected because you have many domains, right? Okay, then since your map F is holomorphic, it's continuous and open. Therefore, the forward images of the closure of the interior of the closure of your wandering domain is going to be contained in some interior of the closure of some the two component. Let's call it UN. Okay, but then if omega is not regular, this means that if you take the interior of the closure and intersect it with Julia set, this is going to be non-empty intersection. But therefore, the forward, we know that the forward images of this set will cover everything except at most one point. Okay. But now this brings us to a contradiction, since if you take the union of these guys, I mean, you can see that they cover much less than everything. They cannot cover everything. That's what I'm trying to say. So being regular is also a necessary condition. And what I use it for, I mean, why is it good for me or for, let's say, us that's working with this, is the following. So if your set is regular, this means that the boundary of your set is the same as if you take closure and look at the complement and look at that boundary, which basically allows you to find a sequence of points outside your domain, such that the accumulation point, I mean, every point on the boundary of every point of the boundary of your domain is accumulation point of this sequence. So imagine if you have a circle, you can find points that sort of go closer, 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 but they accumulate everywhere on the boundary. Yeah. I will anyhow, I'll do the proof later. So don't worry. This is just yeah. Okay. So it's like it's written here. So there exists a sequence of points outside that accumulate error on the boundary. What about the other two conditions? So namely that omega is bounded and the complement of the closure is connected. So this I use, for me, this is necessary in order to use the Runge approximation theorem, or I mean, this is sort of slightly stronger version, but you can also do it with the classical Runge's theorem. But I think, I mean, for my use, this is going to be slightly, it's going to be easier to see what I'm trying to say afterwards. But maybe it complicates the proof a little bit more, not much for an epsilon, let's say. So the first part, you can see this is a classical Runge theorem. So we have, let's say, compact sets K1 to Kn, and which are pairwise disjoint, and whose complements are connected. Right. So this is a classical Runge condition. So in each of these compact sets, you can take finitely many points. And suppose you have a holomorphic functions defined on these compact sets. And then the theorem says that for every epsilon greater than 0, you can find an entire function f, which approximates your prescribed functions on those compact sets. Moreover, you can also prescribe where certain points map, so finitely many points. So what I'm trying to say is that you can say that this map F agrees with your previously chosen maps at finitely many points. So this is the, say, this number 2. But you can also prescribe up to a finite order. So let's say here I choose the order 1. So you can also prescribe derivatives at finitely many points. Okay. And this is sort of the older version. It's sort of hard to find it exactly in this, written in this shape somewhere, but sort of it's a collection of many results from 50s and 60s. Okay, but very similar statement was also given in the paper of Remenko Ljubic of 87, which is called main lemma, if somebody read it already. Okay, so back to the question about necessity of conditions. So it's natural to ask, is the condition that the complement of the closure is connected a necessary condition? I don't know, or I didn't know. So in particular, is the complement of the closure of bounded simply connected for two component always connected? So why am I asking this question? So that if the answer is positive, then my result would imply that we have achieved a complete description of all possible geometries of bounded simply connected one-D ring domains, right? So it's quite a strong statement then. Yeah, I was not able to answer this question. Anyhow, the similar question already arose in 1920s by Fatou, who asked that if F has more than 2 Fatou components, can 2 of these components share the same boundary? Although this question was asked in the category of rational functions, you can also think of it as a question in entire functions in general. And you can think of it that, or you can see that the positive answer to this question, to the second question, gives a negative question to the first one. Because if 2 components share the same boundary, if you take one, you take the closure and take a complement, you'll end up at least with 2 different open components. So that's an advertisement for the next talk. So in the answers to these questions will be given in the next talk by James Waterman. So stay tuned if you're interested. So, okay. Go back. Okay. So I don't see what I have written here. Yeah, okay, it's about the proof now. So how do you prove something like this, and how can you use the conditions that I wrote before? Or what do this, how would you prove something like that? So let omega be an open set as in our theorem, and choose real number R and the strictly increasing sequence of integers Mn, such that these disks centered at these integers Mn's of radius R are pairwise disjoint and disjoint from your omega. Now finally choose a sequence of points in the complement of the closure of omega, which accumulates everywhere on the boundary. So maybe here I can now draw a picture in the bottom. I'll try to do something. Okay, no, not yet. I need to do. Okay, let's hope it works. Okay, no, I have better pictures afterwards. I'll not try to mix, otherwise it's complicated. So anyhow, think of it. You have disks which are sort of disjoint. You have your open set here, and around this open set we have many points that accumulate everywhere on the boundary, and we'll see what you can do with those. So the idea is to construct an entire function with the following properties. So the first one is that this iterates on if you sort of focus on your initial domain omega, are mapped or are contained inside these bounded balls which are going to infinity, right? So this will give you a normality somehow. Okay, the second one, you can make sure that this function has a fixed point, let's say, call it zeta, which is attracting and which is outside your domain. And the forward images of these points that we have chosen initially with this sequence xn is eventually mapped onto this fixed point theta. Okay, and okay, the number 4 is sort of a consequence, so you can make sure that this is univalent. And why does this now apply the geometry of your wandering domain? So why is the wandering domain precisely omega? So look at it that omega is contained, so because of number 1, the omega is contained in the Purdue set. So it's contained in some Purdue component. Maybe that component is larger, right? We don't know yet. Now, 2 and 3 imply that the pre-images of a attracting fixed point or some point accumulate everywhere on the boundary of your omega. Okay, but I mean, this implies that the Purdue component in which omega lies in cannot be bigger than omega. So it has to be precisely in omega. So for those that are here in the audience, think of it, if you have like a disk and all those points that accumulate here are eventually pre-images of some fixed point, right? So there is no way that you can make some larger open set in which your family would be normal, because otherwise you would contain one of those points x eventually, and that would be a contradiction. Okay, so how do we obtain such a function, right? It's a main question. It doesn't fall from out of the sky, unfortunately. So the function is obtained as a uniform limit of a sequence of entire functions, which we construct inductively using the previously discussed Runge's theorem, or a slightly stronger version, Runge theorem. And I'll try to demonstrate this in the case of a unit disk. So the simplest possible case, but the idea is exactly the same if you make more complicated picture. The one, let's say, for example, for Poland. Okay, so how do we start? We start with let's say this blue one. So inside the blue one, the gray area, this is your unit disk centered at the origin, let's say. And this is the boundary. And let's say this is the outer disk. I will call those sets U0, U1, U2, U3, and so on. These disks, the outer one is going to be disk of radius 2, and then disk of radius something less. So that these disks satisfy the following properties. So each one is contained in the interior of the previous one. and their intersection is basically a closed unit disk. So they are getting smaller and smaller and shrinking, and then they're sort of in the limit. They are the unit disk. And in each of them, so in the so let's say after you have chosen the sequence of exhaustion of with open sets, which collapses to your original domain, you choose this sequence of points. You can do that because of the conditions that we have. In particular, for unit disk, this is easy. Just take, I don't know, some irrational rotation and getting closer to the boundary. So you take, for example, this is going to be your x1. This is u0. This is u1. This is u2. This is x2, x3, x4, and so on. And they accumulate everywhere on the boundary eventually. And what I would just want to emphasize here, that so each point is, let's say x2 is contained in u1, but not in u2. And x3 is contained in u2, but not in u3, and so on. Okay, so this is sort of a first step, and then we start constructing the map. Okay. And I'll try to do, okay. Yes, clear drawings. Okay, thank you. That's helpful. And the proof will be just using these pictures, if I manage to. So how do you construct the first map? So let's say you take this U2, U1, sorry, this is U1. This gray circle is U1. The smaller one in here, this is the unit disk, right? And then you can prescribe what you want on certain sets, on compact sets. So this is going to be my one compact set. This is another compact set, and this gray area here is another compact set. So I can say, okay, on this compact set, on the blue one, I want it to be a translation, or approximately a translation, right? On this one, on point number 3, I want it to be a fixed point. And you can also prescribe the derivative if you want. I mean, it's not necessary, but just for sake of it. This is what you can do. And then x1, you want it to be mapped onto this point, right? And then we are exactly in the Runge's theorem, right? Because all of these sets satisfy the conditions. So their complement is connected. These sets are disjoint. We have holomorphic functions on them. So therefore, we can find a holomorphic function f1, which satisfies all these conditions, namely that it's almost translation on this disk, that it maps x1 to point 3, which is a fixed point, and has a derivative 1/2, let's say, at that point. That's like what is written here. Right? So this is the first step, and this is how you obtain map f1. Okay. So how do you proceed now from here? Okay, now maybe I have to move this slightly. Sorry. So we have already found map f1. Which maps, I mean, which does whatever we want. Now, in the next step, we want to construct f2. So how do you do that? You take a slightly larger disk. So this is the disk of radius 4, on which you want to approximate already constructed map, f1. So you want f2 to be close to f1 on this set. Let's call it, what is it here? It's K3. 1, K3. So because there we already prescribed there's going to be translation, that point is going to be mapped into itself. It's going to be a tracking point, and the x1 is going to be mapped into this point 3. And we can do precisely that with the new map. But then we have a freedom of choosing what will happen on this slightly smaller set here, right? delete this. Okay, so what is this gray area now? Now the gray area is slightly different than the one before. Different in the sense that we took the set U1, so the slightly larger disk. Now we go one step in. So we take the slightly smaller disk. So before this was U1, and this is the image of U1. And the one in here, it's U2. And this is the image of U2 under F1. And we do and we take this gray one for our second compact set on which we're gonna try to prescribe our map. And we can do that. And we say, okay, let it be a translation by 4 or by 8, whatever, I have it here. And this is the image of the next point, x2. If you see, here is the next point, which one of the sequence that accumulates around. This point is mapped in here. But now I can sort of say this point has to be mapped on the fixed point, right? And I can achieve this by approximating again. And I get the fixed point, I get the map F2, which does exactly what I want. So it says this point is mapped here. This point is mapped, this point is mapped here by F by one iterate, and the next iterate is going to be mapped on this fixed point. And on the unit disk is always a translation by 8. And then you continue with this procedure over and over again. The thing is that this yellow circle is keep increasing. And if you're making a better and better approximation, therefore you get a sequence of map which converges uniformly on compact subsets. Right? So it's something that one has to verify a little bit, but not much. Okay, so this is sort of next step. I will not explain it, but that's what I want to say. You have the slightly larger disk on which you approximate the previous map and so on. Okay. To clear this. So you can also achieve, that was the example of escaping wandering domain. You can also make it oscillating with similar idea, having points accumulating on the boundary where you put them sort of eventually you want to map them to a fixed point. But the dynamics is slightly more complicated, so you have to work a little bit more on fine-tune this approximation. So how the sets move and so on to make sure that you get oscillation. But it's possible to obtain an oscillating domain as well. So if somebody wants to know how to do it, read the paper or ask after me later. Yes, but the idea, the proof, it's basically the same. So the main idea of what I want you to sort of just get it is that you have a set, you can have a sequence of points converging towards the boundary from the outside. And if you can make sure that you find the map on that the iterates on your domain are sort of, it's a normal family, and that the points that you have selected before are mapped to some fixed point, for instance, subtracting fixed point, and this will sort of define your geometry. Okay, I'm doing time. Okay. Okay, so I have much more time than I thought. Yeah. So funny story is that you might think that usually ideas come from one dimension before somebody starts working in higher dimensions, right? So interesting, I think this was done in the opposite direction. So I was thinking about this problem, how to make a wandering ball first for automorphisms of CN. Let's say for C2 for simplicity, not to complicate the matter. Just because the way of finding wandering domains for automorphism is a bit difficult, and especially saying something about their geometry is quite still, it's a big mystery. And as you will see, the idea of the proof is basically the same. Just, I mean, things are more complicated in some sense because without automorphisms, you have more restrictions, of course. Just to briefly explain what's the result there, I need to just remind everybody about some basic definition. What does polynomially convex hull means? I guess people don't work. I mean, many of you might not know this. So what is the polynomially convex hull of a compact set K is defined as a set of all points in the Euclidean space such that the modulus of P of Z is less or equal than the sort of supremum of your polynomial P over this compact set for all polynomials P. And we say that the set K is polynomially convex if the hull, if it coincides with its polynomial hull. So, of course, this notion is not only known in dimension n, I mean 2 and higher. It's also dimension 1. It's well defined. But in dimension 1, this is exactly. I mean, we have the following analogy, right? So the set is polynomially convex if and only if its complement is connected. So it's the thing that it's used in Runge's theorem, right? So the thing is, the polynomial convexity in dimension 1 is basically saying you don't have any holes inside your compact sets. So unfortunately, in higher dimensions, there is no such nice geometrical characterization of polynomial convex sets. We can have sets with some holes as well. So it's non-trivial topology. So things are slightly more complicated to verify if something is polynomially convex or not. Which one?
Polynomially convex in the plane. This is what's called full.
I
usually.
think, yeah, they call, yeah, I think, right. You fill all the holes, basically, yes, yes.
And so you're saying here that this polynomial condition you put upstairs, it's also, so how would this translate in one dimension?
This one? This
so
one?
In one dimension, it's that all polynomials in.
So you have,
I mean,
so you have polynomials, I mean, one variable.
yeah.
And you say that it contains all the points. It's basically maximum principle, I guess, right?
Ah, okay, okay, of course. Okay, thank
Okay. So what's the result? The result is that let omega be an open, bounded, regular set whose closure is polynomially convex. Then there exists an automorphism of Cm with an escaping or oscillating wandering domain, which is equal to omega. So if you can sort of imagine, if you forget, or if you replace the word automorphism with transcendental, and if you replace the word polynomially convex with what we had before, so the complement of the closure is connected, which is, you see, equivalent stuff like this one. So it's basically the same statement, but for automorphisms. Okay. So what are, just to give you examples of what are some polynomially convex domains? They're all bounded convex domains, satisfies these conditions. So ball, ellipsoids, and so on. We have many examples. Less trivial, the one that have trivial, non-trivial topology. Think of it. You can get them in the following way. So let's say take any totally real compact manifold. Just think of it as a, let's say, a curve in the space Cn. Think of it as a curve. You can always perturb it a little bit so you can make it polynomially convex. And then you can take a tubular neighborhood of this set. And this is going to be a polynomially convex set which satisfies these conditions. But I mean, now I was talking about the curve, but you can do it with any totally real compact manifold as well. So, I mean, there are many non-topologically trivial examples that you can achieve this way. So just in words, the idea of the proof is essentially the same. So you have a domain, you take a sequence from the outside that accumulates everywhere on the boundary, and you want to sort of make sure to construct an automorphism which does what it did before. So it moves your set out to infinity somehow slowly, but in the normal way, and that it maps all those points somewhere else such that do not interact with your initial with the orbit of your wandering domain. But there is one major difference in the proof. So you remember how we construct the map F. So we construct the map F using the Runge's theorem. So we construct a sequence of maps, the sequence of entire functions that converges uniformly. And we know that, I mean, the limit is going to be either a constant or an entire function. And that's great, right? So we get entire function. But in the case of automorphisms, you will get a convergence, but the map that you converge to does not need to be automorphism. So there's surjectivity can be lost. And this is not, okay, this is hypothetical, but this actually does happen. So you have, I mean, you can find examples of maps or sequences where this converges. For example, if you're familiar with Fatu-Bieber-Bach domains, so these are domains. So Fatu-Bieber-Bach domains. Domain. So this is the domain omega inside Cn, which is not Cn. Sorry. Yeah, I think I will lose too much time with that. So the idea is that omega is biholomorphic to Cn, right? And these guys are usually achieved as obtained as a basis of attraction of a attracting fixed point. Oh. Okay. I mean, anyhow, I think have it. Oh. That's fine. I mean, I will write here. So I'll write here. Okay. Laszlo, can you see now?
Yes, thank you.
Okay. Okay. Oh, so you can see, yeah. So these guys can somehow be, I mean, achieved always with as a basis of attraction of an automorphism, and there's the usual way how you get these guys. Okay, so but there's a way with, I mean, there's, well, okay, close. So one has to put some more effort to prove that you actually can get convergence towards an automorphism. It's not a trivial part, but it can be done. And the key ingredient for the proof is the similar approximation theorem as the Runge theorem for entire functions. We have something similar for automorphisms, which is called approximation results of Anderson-Lambert theory, which again, if you are given compact sets, let's call it K1 to Kn, which are pairwise disjoint, and such that all but one are star-shaped. Just think of it that they are balls, for example. And on each of them, you have your map, let's say, defined automorphisms. So you say on X1, on K1, I want this kind of action, on K2, I want this kind of action, and so on. And there's another condition that the images under these maps are pairwise disjoint. Right, so these are sort of natural conditions. So if you have two compact sets, and if you prescribe, I want the image on this one to be like that, and image on this one be like that, it cannot happen that the images intersect, right? Otherwise, it's not going to be injective, so it's not going to be automorphism. So that's why there's condition they have to be disjoint, the images. So and the last non-trivial condition, which is not that trivial to check, to verify, is that these sets, so the union of these sets K and their images are polynomially convex. So this is something that you have to really be careful how to work on. That's the harder part, I would say. So then for every epsilon, there exists automorphism G, which does exactly what you want on prescribed compact sets and at finitely many points. Okay. I'll try to stop here. Yeah, thank you.
Okay, thank you very much. Some questions from the audience, please raise hand. Wait a second, for the microphone.
Thank you. Do you have an idea what could happen if you replace polynomially convex with just holomorphically convex, which is
Again, sorry.
If you replace in your theorem
Yes.
an assumption polynomially convex by holomorphically convex whole.
Where in this
In your last theorem. Yeah.
is gonna be the same, right? So
Nope.
wait.
Nope.
Well,
It's gonna be harder.
wait
I'm just asking you if you have a vague idea, because
no, holomorphically isn't. Wait, am I missing something? So since polynomials are dense.
No. It's holomorphic convex is a natural domain of holomorphic function in Cn. So
Domain of holomorphic. Okay.
Yeah.
Maybe.
Okay, if you haven't thought of it, I think it's just a natural extension. But okay, thanks.
No, but I would still think. I mean, if I'm missing something with the definition, but if you replace polynomials with holomorphic function, and every holomorphic function can be approximated with a polynomial, then the definition of holomorphic hull and the polynomial hull is the same, right? But I know what you mean. I mean, you want to say what if you replace with the domain of holomorphy? Then that's a different thing. Yeah, I didn't thought about that.
Okay, any more questions?
Is the degree in your construction of escaping wandering domains, is the degree of the transcendental function you get the degree of the translation in your case? So is the map, does the map F have degree 1 because H has degree 1?
Yes.
If you replace H by a Blaschke product composed with a translation, will you then have, you can do that, right?
So I think we asked this question at some point.
So if you can do that, the degree will also be the degree of that map.
Degree of that map. So you have, if we just go slightly back here so that people know what we are speaking about. So when you do your approximation here, where we took this open set here and we sort of make a translation by H1, and then like this was approximated by F as a translation, but you have a lot of freedom of choosing what this H1 is. I would have to do some fine tuning, but I think that if you take sort of finite Blaschke products and play around, maybe not taking defining this sequence Xn in the start, but do it in every step. So in every step, you can select some points and do it. So don't choose this sequence of points in advance, but do it inductively.
On the way, yeah.
I think on the way you can do that. You should be able to manipulate this thing. I think so.
Thanks.
Okay, maybe some questions from online participants. Okay. Yeah.
Maybe I can ask a brief question. I think I missed the first part of the talk, so my question may be silly. So in the second part, that is example that you have of wandering domains, could you also use this technique to build some like fixed or periodic domains with prescribed geometries?
Fixed? No, I don't think so, because I mean the key of this approximation is that you move things far away and work there and live. Yeah, no, I mean I don't think so that you could use any approximation stuff on some bounded for bounded orbits or something like that. If you want to do a periodic set, periodic components or something like that.
So is there any kind of techniques that allows you to build, like, to prescribe the geometry for a fixed or periodic photo component?
Oh, you mean for the invariant, let's say? No,
Yes.
yeah, I don't think so.
You don't think so?
I don't know. I mean, at least with the approximation theorem, I don't think you can do it.
You see.
Yeah.
Okay, thank you.
Okay, we have one more question from the audience.
So do you think you could make them unbounded if you changed Runge's theorem by, say, Aracelian's theorem?
Good question. I have to think about it, but yeah, I don't know it from the top of my head, but maybe. So the Carrion says that, do you remember what is it like if you have an open set that has such certain geometry at infinity, the nice one, right?
Yeah, it's connected and locally connected at infinity.
Right. Yeah, you might. I will have to let me think for a few minutes and then I will let you know.
Thanks.
So I think maybe I discussed this at one point with David and James, who may remember more what we discussed. I think our conclusion was that generally you could do something with Aracelian's theorem, but it's not clear. You might need some kind of conditions that the domain isn't too wild as you go out to infinity, because you want to sort of your approximation by something that you can get. So you can get constant approximation by Aracelian's theorem. Sometimes you can get a better approximation, but somehow you want your approximation to not destroy completely kind of what's going on. Probably you can do something, but it's not clear how general you can go.
Yeah.
Okay, thank you once more.
Thank you.
The next talk is